Okay. You tell me what law this is, whether it's Newton's first law, Newton's second law, or Newton's third law. You don't know what Newton's third law is, so that's a big hint for you. Okay, so Mr. Walton is riding on, I don't actually know how to draw this. So there we go, perfect. So Mr. Walton is riding on a scooter or a motorcycle or something like that. And so he's going this way. And a little ways down the road, he doesn't see it because he's not really paying attention. He's texting, he's distracted, he's whatever, okay? There's a giant pothole in the road. Mr. Walton drives along. Mr. Walton drives along, boop, 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 okay? The front wheel of his scooter digs into the pothole. What's going to happen to the scooter and what's going to happen to Mr. Walton? So what's going to happen to the scooter? The scooter is going to stop. Why? Why is the scooter going to stop? Ooh, because something is applying a force on the scooter. Would you agree? The scooter runs into that pothole and something applies a force on it. Therefore, the scooter will accelerate. In this case, is the scooter experiencing positive acceleration or negative acceleration? Negative, it's slowing down. It's going to stop real quick, right? Okay, now, what's going to happen to Mr. Walton? Is the pothole applying a force on Mr. Walton? No. So where's Mr. Walton going to go? Whee! Mr. Walton's going to go over the top of the handlebars, and he's going to face plant onto the road, isn't he? So, for rule number 1, always wear a helmet. Rule number 2, never text and drive, right? Which law is this? This is Newton's first law. This is talking about Mr. Walton has inertia, and in order to stop Mr. Walton, in order to change Mr. Walton's speed, you have to act on it with a force. Okay, so some external force has to act on it. Because there is no external force acting on Mr. Walton, essentially, it means Mr. Walton's speed is not going to change, essentially. Is there a little bit of a force acting? Yeah, sure, whatever, that's fine. Okay, so this is Newton's first law. Perfect. It's the same thing as have you ever been driving in a car and have you ever been driving like a little bit too fast as you go around a bend? And so your car feels a force this way because the tires and the friction between the tires and the road are directing the car that way, right? So the car travels with the curve, but what does your body want to do? It wants to go straight. So because the car is going to the left, it feels like your body is doing what inside the car? It feels like it's going to the right. Does that make sense? But your body's not going to the right. It's staying straight. So imagine there was a bend in the road, okay? And so Mr. Walton is sitting in a car. Mr. Walton's sitting in the driver's seat of the car. As the car drives down the road, you turn the steering wheel. there's a force applied on the car. It's actually the force of friction between the road and the tires, and it causes the car to bend around the road. So your body, your car is going to be like that. But what path does your body want to take? Yeah, because the road isn't applying a force on your body, it's applying a force on the car. So you want to continue in a straight line. Does it make sense that the car's going to the right, you're going straight, but it feels like your body is being pulled to the side of the car? Feels like your body is being pulled, but your body's not being pulled, the car's being pulled. You're staying not stationary, but you're staying in the same trajectory. It's just relative to the car, it feels like you're being pushed to the side. So that's Newton's first law. Both of those cases are Newton's first law. What is Newton's second law? Do you remember? Newton's second law is purely mathematical. It is the net force acting on an object is equal to the mass of the object times the acceleration of the object. That's it. That's Newton's second law. If you want to accelerate at a higher rate, you need a higher net force. That's all. Now we're going to talk about Newton's third law. And this is a little bit difficult. Can I have a volunteer come up to the front for me, please? Ryden, come on up here. Thank you. Okay, this is a little bit difficult. You got to kind of stand on, like normally you would have your weight distributed all across your foot, right? But what I want you to do is I want you to stand with almost 100% of your weight on your heel. Does that make sense? Yeah. So it should feel very uncomfortable. Okay, now, do you want to push me or do you want me to push you?
Yeah, you can push me.
All right, okay. So don't smash your head against the ground. Please, that's my only request. Ready? Yeah. I'm going to do the same thing. I'm going to stand with my weight on my heels, essentially. Okay, ready? 3, 2, 1, go. Holy cow. What just happened? But I pushed him. I pushed him. Oh. So when okay, let me get this straight, okay? I'll try it again. And what I'm trying to do is I'm trying to put my weight on as small of a surface area as I possibly can. So when I push Ryden, does it make sense that Ryden pushes back on me? I'm applying a force on him, but anytime you apply a force on something, it applies a force back on you. Are you good? Yeah. Thank you. You can go sit down. This is often called action-reaction. And so the way that you might have heard it before is for every action, there is an equal and opposite reaction. Again, we kind of need to think about things in space, because in space we have very few forces acting on us, right? There's essentially no friction. There's essentially no gravity when we think about it in the way that we're going to think about it, which is not technically true, but whatever, that's fine. So for every action, there's an equal and opposite reaction. So let's think about this for a second. Imagine we're out in space and we've got an object. This object has some sort of velocity. It's going in that direction. And then there's an object, another object that's totally stationary. So this is object A, this is object B. Object A is traveling towards object B. Since we're out in space, It can't really slow itself down. It can't really speed itself up. It's not in contact with any surfaces. It's not really doing anything, whatever, okay? When A collides with B, is A going to apply a force onto B? Yes. So let's draw some free body diagrams. This is going to be a free body diagram for A, and this is going to be a free body diagram for B. So, okay, A is going to bump into B, so B is going to feel a force. What direction is B going to feel a force in? Which direction is going to go? It's going to go to the right. So we're going to draw a force that way, and we're going to call this F A on B. Do you understand why we're calling it A on B? So force of A applied on B. Okay, well, how do you know A is going to apply a force on B? What's going to happen to the velocity of B? It's stationary right now. Is it going to be stationary after the collision? No, right? A is going to cause B to accelerate in the forward direction. Well, what's the only way something can accelerate? You have to apply a force on it. So clearly A is going to apply a force onto B. This is the free body diagram for B. But what's going to happen to A, Chris?
Do they have the same mass?
Do it? Doesn't matter.
Oh, it doesn't matter?
Nope. Is A going to slow down? If Mr. Walton and Ryden were out in space, and Mr. Walton collided with Ryden, would Ryden accelerate because of that collision? And would Mr. Walton slow down because of that collision? It does not matter the mass. The mass could be 1,000 to 1, could be 1,000,000 to 1, they could be equal. All that matters is how much energy is transferred or how much momentum is transferred. And you'll talk about that at the physics 30 level. Collisions and stuff, that's physics 30. So, well, Mr. Walton, or A, what's it going to do again? Sorry, I forgot. What's it going to do? It's going to slow down. So what direction is A going to feel a force? It's going to feel a force in this way. And what is that force going to be called? Force of B on A. And what do we know is going to be, what can we say about FB on A and FA on B? Those forces are equal to each other. They might not have the same result in acceleration because they might have different masses, right? If something super, super, super duper heavy, its velocity will change by a tiny amount because it's got lots of inertia, right? If something's really, 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 really tiny, it's got very little inertia, it'll have a really big change in velocity. But all that matters is that these two forces are the same magnitude. Are they totally identical forces? No, because clearly they're going in opposite directions. They're going in different directions, right? But the forces, their magnitudes will be equal. This is what we call an action-reaction pair. It's a pair of forces that always occur at the same time in opposite directions, but their forces are equal in magnitude. Now, why does this matter? Well, it matters for a bunch of different reasons, okay? So we're going to talk about a couple examples of where, we're not going to talk about a lot of math, but we're going to talk about a couple different examples, okay? Mr. Walton, would you believe it, has literally never fired a gun before in his entire life. Has anybody ever fired a gun? Some sort of a 22 or a handgun or, yeah, okay, all right, nice. Okay, Hunter, when When you fire a gun, do you feel anything? Yeah. Do you know what the name of the feeling that you feel when you fire a gun is? Recoil. So good. Okay, Mr. Walton's going to try and be a crappy artist, but he's going to try and be a good artist, but whatever. Bum 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 bum. Are we good with this? Do you understand what I'm talking about? Okay. Hey, that's not bad. Yeah, even a blind squirrel finds an acorn every once in a while. Okay. So what's going to happen here? When you pull the trigger on a firearm, inside the gun, there's a tiny little explosion. The explosion applies a force on the bullet. But who else feels that force? Yeah, well, the gun. Good. So, the bullet, which direction is it going to go? That way. The gun, which direction is it going to go? That way. And what is behind the butt of the gun? You are, right? So the more powerful this explosion is, right? Obviously, the greater the acceleration of the bullet will be, but also, what else is going to accelerate at a high rate? The gun. So the gun is going to come back and you're going to feel that force, right? So, okay. Now this is kind of crazy, but if you were out in space, could you use a gun to propel yourself? If you had a gun, like let's say you had a shotgun, right? If I'm out in space and I can't reach my vessel and nobody's in my spaceship to be able to throw me a rope or something like that, but I have a shotgun, okay? And it's got unlimited ammunition, okay? Shut up, whatever. So you've got a shotgun and you're out in space and my ship's over there. So how could I get to the ship? What do I got to do? So I got to aim away. I got to take the butt of the shotgun, place it in the center of mass, my center of mass. And when I shoot, the pellets go that way. But what else happens? Me and the shotgun, we go this way. And so if I had one shot, right? Click, boom, I go this way. Let's say I'm not going fast enough. What could I do? Do it again, right? Does that make sense? Hey, what have we just created? We've created a rudimentary... Yeah, until they hit something, right? Yeah, Newton's first law, until they're acted on by an external force. Yeah. Oh, yeah, I'll take that chance all day. Yeah, I got the chances of that happening are 0, basically. Hey, what have I just made? I've made a rudimentary rocket. Have I not just made a rocket? Yeah, what does a rocket do? I don't know how to make a rocket. Okay. Is that a rocket? Sure. Why not? Okay. So in order for the rocket to go up, what does it have to do? It has to, a rocket is quite literally a gun that is, instead of firing bullets downward to make it go upward, what is it firing downward? It's firing exhaust from a really controlled explosion. So it's burning something the exhaust is going down. So air molecules are going down, but because they're pushing air molecules down, what happens to the rocket? It goes up by Newton's third law. So if you push enough air down fast enough, you will overcome the force of gravity. Absolutely you will. Now the problem becomes you need such a large amount of gas or exhaust to leave your rocket that you need an incredibly complex design, and it needs to be very well engineered, and anything that goes wrong could be immediately dangerous to anybody in the rocket or surrounding the rocket, right? But the exhaust goes that way so that the rocket can go that way. And yes, you out in space with a shotgun are considered a rocket. Okay? It's the exact same principle. So what are some other problems that are associated with this? Well, okay, let's take a look at one that actually does involve a little bit of math. Mr. Walton applies a force to the following objects. Sorry. Object C starts to accelerate at a rate of 2.79 meters per second squared forward. We're going to draw a diagram just so that we're all on the same page of what this actually looks like. So we're going to have three objects back to back to back. So object A, object B, object C. The masses of A, B, and C are as follows. The mass of A is 5.00 kilograms. The mass of B is 10.0 kilograms. And the mass of C is 8.00 kilograms. These objects, think of them as boxes or whatever. They're sitting on a smooth, frictionless surface. Does such a surface exist? No. But we can approximate one on the Earth. We can try and get really close to it. Okay, so Mr. Walton is going to apply a force. What am I pushing on? What am I pushing on? Ooh, am I pushing on A, B, and C? No. I'm pushing on A. A is pushing on B. B is pushing on C. Good. Are we okay with that? So, now what we're going to do is we're going to calculate the force of B on C. That's what we want to do. Calculate the force of B on, sorry, no, C on B. Oops, sorry, C on B. Of C on B. C on B. Whoops. Classic dyslexia. Okay. Well, this should be pretty fine. This should be okay. And we want a specific force, so what are we going to have to draw? Let's draw some free body diagrams. How many free body diagrams should we draw, just so that we're really thorough? Well, we should probably draw 3. So let's draw the free body diagrams for A, for B, and for C. And let's not skimp out on the details here. Who do you want to talk about first? Do you want to talk about A, B, or C? A, sure. What are all the forces acting on A? Okay, so here's A, and force applied. Which direction is force applied? Where should it be pointing? Yeah, there we go. So F applied. Good, APP. What other forces are acting on A? Force of gravity, lovely. Force of gravity. The normal force, fantastic. Any other forces? It's a frictionless surface, so there is no friction. Josh? Well, we know if B wasn't there, would A move faster or slower than it currently is? It would move faster. It would accelerate at a greater rate, right? But the fact that B is there, would you agree B is inhibiting the acceleration of object A? Yes. So absolutely, B is applying a force on A. So this is FB on A. Love it. Okay, that's all of the forces that are acting on A. Okay, no problem. Let's go ahead and let's talk about B. Let's get the 2 obvious ones out of the way. What are always... Yeah, okay. So force of gravity, right? 9 times out of 10, there's something related to these forces. Gravity and normal force. Okay, cool. Are there any other forces acting on object B? Is there anything pushing it to the right or pushing it to the left? Okay, so A is pushing on B. Which direction should that go? To the right, forward. So that's F A on B. Is there anything slowing B down? Is there anything? Yeah, absolutely. C is pushing back on B. So F C on B. Okay. And then finally, the free body diagram for C. What 2 forces are there? FG and FN, sure. Any additional forces? Good, the force B on C. C is being pushed to the right. F, B on C, not Beyonce. The force of Beyonce. Okay, is there any other forces acting on C? Nope. Okay, let's take a look. What do we want out of this thing again? What are we looking for? We're looking for the force of C on B. In order to figure that out, we need to know 4 things. We need to know FG, FN, but what can we kind of do with FG and FN right now? Just, yeah, because they're equal and opposite. Is this box accelerating upwards into the sky? No. Is it accelerating downwards into the earth? No. Okay, so Fn and Fg cancel each other out. That's easy. The net force in the vertical direction is 0. So just ignore Fn and Fg. But in order to figure out this force, what 2 other things do we need to know? We need to know 2 other things. You need to know Fa on B. Do you know that? No. Okay, so we're kind of poop out of luck there. And then what else do you need to know? The F net in the horizontal direction for B. Do you know the F net of B? You do. It's a sneaky way. What information did I give you in the question? I gave you the acceleration of which object? Of object C, but these objects are moving as one system. So the acceleration of C is the same as the acceleration of B and the acceleration of A. So F net, in order to calculate F net, what two things do you need? You need acceleration and mass. Do you have the mass of all three things? Do you have the acceleration of all three things? So yes, you do know the F net. You do know the net force. But it's this stinking little FA on B. We don't know what FA on B is. Could we rearrange for it? Well, don't write this down. Let's just do it really quickly. So this is for object B, okay, F net in the x direction is the positive force minus the negative, if we're assuming that's positive. So FA on B minus FC on B, okay? Now, if you're sick of writing A on B, at this point in time, I feel like we've written it enough times that a lot of people will actually write FAB. This means A on B. Is that okay? That's a lazy way that physicists get around writing the word on all the time. Okay, let's think about this. Hey, do we know what F net is? Yeah, we do. We can calculate it really easily. It's mass times acceleration. Do we know what A on B is? No. Do we know what C on B is? No, you have a system of equations with two unknowns. Can you solve for a system of equations or an equation with two unknowns? No, you can't. Dead end. Anybody else? You might be able to, but remember, if we think of this as a total system, which absolutely is helpful, sometimes that's absolutely helpful, but now the force of C on B is an internal force, and you cannot calculate it by looking at the system as a whole. So that absolutely would be helpful sometimes, but in this case, it's not helpful. So I'll delete those later. Take a minute, talk to the people beside you, try and figure out how could you get the force of C on B. We already know using free body diagram of B is not going to work. We know that using a system is not going to work. Take a minute, physically talk to somebody else. Turn around and talk to somebody else. Any thoughts? Ooh, okay. So we want C on B, right? But how would this help? How is that going to help us? You're right. What can we do to help us find C on B?
I was thinking we should calculate for either this or this, because I'm pretty sure we already have FG.
Yeah, we have FG, which means we know FN. They're the same. FB on C, that's an action. Where's its reaction pair? Where's the pair force of B on C? Nope, swap these letters. Instead of B on C, they're the same force. So if we want that, we just have to get that. Okay, let's try this. Somebody tell me, somebody talk to me about a strategy. We want C on B. What are we going to do about that? Write in.
Can you solve for force B on C, and since B on C and C on B should be equal,
is, so this is a push, right? Yeah? Well, that's an action. For every action, there's an equal and opposite reaction. That's an action. Where's its reaction pair? This and this are the same size. They are the same force, just in opposite directions. So if you solve for B on C, you immediately know the magnitude of the force of C on B. They are the same force, just in opposite directions. So let's go ahead. So we're going to, which object do we have to solve for then? Object C. So we're going to say, so for object C, so we're going to go F net in the x direction. Well, what's the only force in the x direction for this thing? FB on C. So again, you can write FBC, that's fine, B on C. Okay, well, what's F net always equal to? So mass times acceleration equals FB on C. Okay, well, you know the mass, you know the acceleration. Is this actually really easy? Yeah, it's incredibly easy. So FB on C is just that mass. Whose mass? What mass? Which mass? When you're looking at the free body diagram for C, so it's the mass and the acceleration for C. So C had a mass of 8 kilograms and an acceleration of 2.79 meters per second squared. And it was positive, right? 8 times that, I don't know. 22.32 newtons. And that force is to the right. Okay, well, we know the force of FB on C, so immediately what is the force of FC on B? Good. Therefore, have you ever seen that before? 3 dots in a triangle. Therefore, FC on B is equal to 22 point, how many sig digs should we have? 22.3, one decimal place, right? Newtons to the left. Because they are action-reaction pairs. Okay, could we have, now that we found this action-reaction pair, could we have found the force of A on B? Yes. So then we could have found the force of A on B, which is the same as B on A. And now that we found B on A, what else could we find? The applied force. And would that be a pain in the butt? Maybe a little bit, but it's actually not that bad. It's just rearranging a couple F net equations. No big deal. Okay? What? What? Are we good? Okay, all right. Hoo-ah. Okay, let's try another one. So Mr. Walton pushes on the following system. With a force of 320 newtons to the right. And we're going to define a bunch of stuff. So we're going to draw a picture. We're going to define a bunch of things along with the diagram. So here's a surface. Here's A. Here's B. I'm applying a force to the right of 320 newtons. The mass of A is 42 kilograms. The mass of B is 17 kilograms. And the force of friction on A is 32 newtons. The force of friction on B is 75 newtons. They're different objects. They have different surfaces. They're in contact. They're maybe made out of different materials, so they have different forces of friction. Chris? How do you know the friction of the floor? We'll talk about that in a couple days. But what you have to do is you have to do a bunch of testing. So you have to physically test objects in the real world, and you have to see at what force is required to get this thing to go a constant speed, essentially. And then you can figure out what's called the coefficient of friction between this material and that material. You can calculate the rate of acceleration of a sliding object or a rolling object. We'll talk about it later. Yeah, we'll talk about it later. Okay, cool. So what I want to know is, very first thing, what is the acceleration of block A? So let's think about this for a second. When we draw the free body diagram of A, let's go ahead and draw the free body diagram of A. It's asking something about A, so let's go ahead, draw the free body diagram of A. As always, there's a force of gravity. There's a normal force, sure. What else is acting on A? There's a force applied. Which direction is the force applied? To the right, there's a force applied. We know the force applied, okay, so that we're good. What else is acting on A? Chris? Okay, so friction, I'm pushing to the right, so where's force of friction? To the left. So there's a force of friction to the left. That's force of friction on A. Are there any other forces acting on A? Yeah, so A is bumping into B, which means B is bumping into A. So there's a force of B on A. B, A. There's 5 things. In order to get the acceleration, where's acceleration always? Where is it hidden? F net. So I have to write an F net equation here. But in order to get the acceleration of the object, I need to know all of the other forces in the horizontal direction. Do you know the F applied? Yep. Do you know FF? Yep. Do you know FB on A? Nope. So we can't use this. Can't use this to get the acceleration of that object. So what are we going to do? We could write a free body diagram for B. What's the free body diagram for B? Well, let's do this quickly. Force of gravity, force normal. What's pushing B to the right? FA on B. Is there anything preventing B from, is there anything slowing B down? Ooh, the force of friction acting on B. Okay? So again, in order to get, what do you want out of B? Because the question is asking about A, but okay, sometimes it's useful to talk about B first. What do you want out of this that might help you over here? Okay, FAB. You want that. That's what you want. Okay? So what do you need in order to get that? You need the force of friction on B. Do you know that? Yes. What else do you need? F net for B. So do you know B's mass? Do you know B's acceleration? No. So we don't know F net. Shucks, huh? Whatever could we do? Yeah, you could actually take both F net equations and you could combine them using substitution. You could solve this as a system of equations. But we already know how to work around a system of equations. We already know how to work around adding two equations together. We worked around that all day yesterday. If we make these two blocks into a system, then what can we do? We can avoid all internal forces. So now, let's treat it like a system. So, do I care about vertical forces right now? No, so we're just going to ignore vertical forces. I need you to understand they're still there, we just don't care about them. So, there's a block A, and then there's a block B, okay, and they're attached. But what we're going to consider them to be is we're going to consider them to be a system. So, are there any forces pushing the system to the right? F applied. I don't know why I capitalized the A in applied. Are there any forces, external forces, slowing the system down? Force of friction on what? A, and force of friction on B. What about FA on B and FB on A? They're right here, aren't they? And do we care about them when we treat this as a system? No, they're internal forces, so we don't care about them. I want to be really clear. If you're trying to get the acceleration of a single block, what else could you solve for? Instead of getting the acceleration of a single block, you could get the acceleration of all of them, because they're all the same acceleration. So all we care about is the acceleration of the system. So let's go ahead and let's write an F net equation for this. F net for the system is all the positive forces minus all the negatives. We're assuming this is positive and that's negative. So we're going to go F applied minus force of friction on A minus force of friction on B. What do you want out of this? Acceleration. Acceleration's hidden inside F net, so we got to break it down a little bit. Mass. Mass of whom? Of the system. You drew a free body diagram of the system. So mass of the system times the acceleration is F applied minus force of friction on A minus force of friction on B. So then you just divide by the mass of the system. Acceleration is all of those forces divided by the mass of the system. This is not, the math itself was not difficult. It's knowing when to use a system that helps us. So F applied is 320 newtons. Minus the force of friction on A, what's that? 32 newtons. Minus the force of friction on B, what's that? 75 newtons. Divided by the total mass, 42 plus 17. Is that what it was? (42 plus 17), yeah. So 57 kilograms. 59. Good math, Walton. Are we good with 3.6? 1, 0, 1, whatever. So 3.6 meters per second squared to the right. If you want to get the acceleration of the system, or if you want to get the acceleration of a single object, often it's better for you to just solve for the system as a whole. If you want to try and find an individual force, FB on A or FA on B or something like that, then unfortunately, you have to break it up into individual free body diagrams. Practice. What did you do yesterday? Yeah.
I'm just asking because he.
Oh, okay, yeah. You're welcome.
I did steal
Why are you lying?
I was writing in the car at 1:30.
It's like, I've been drawing of him. Oh, no, he's here.
Yeah, it's classic. It's like.
It's kind of silly. Okay, right? And then, it's Deadpool and the Avengers, right? Deadpool and the Avengers. Why is Spider-Man here? Oh, Spider-Man.
Okay. I know the answers are not on here, and I apologize about that, but also I'm going to put the answer keys on the 2 lab benches in 20 seconds, so you do have the answers available. That's the thing that you have available for you. These questions are almost total mirrors. They're almost identical to the questions that we had in our notes, so just let me know if you have any questions. Please just work hard for like 10 minutes. If you need to take a break right now, if you're like, holy cow, I'm falling asleep, or I can't do this, I need to get up and go to the bathroom, then get up and go to the bathroom. Get up and take a walk around the lab. Just do a lap. Challenge Mr. Walton to a push-up competition, right? Do something to get the blood flowing, come back in here, then work hard for 10 minutes.